Craig's the director of the Center for Resilience in Agricultural Working Landscapes at the University of Nebraska-Lincoln. So take it away, Craig.
Can you hear me? Well, thank you for having me today. Happy to be here. I am the director for the Center for Resilience in Agricultural Working Landscapes at the University of Nebraska, and professor in the School of Natural Resources. And I moved into that position a few years ago after heading the Nebraska Cooperative Fish and Wildlife Research Unit for a couple decades. So now with the university. And I want to talk to you today a little bit about the Platte and change in the Platte, pressures on the Platte, and resilience. Obviously Platte's the topic today, and we've heard the idea of resilience come up many times. So I'm going to talk about resilience and resilience on the Platte River. And this is a lunchtime talk, so I'm not going to throw out data at you or anything. I'll keep it pretty light, although when we talk about some of the challenges happening to the Platte, to the state, and the world right now, ecologically, it can be a little challenge to be super upbeat. But there's a lot of really good work going here on the Platte, and some excellent people devoting their professional careers and non-professional careers towards improving this river, and that's great to see. So with that, I will, if I can find the flipper here. Here we go. Oh, I like that. All right, so I'm going to sort of put the Platte in context of challenges we have, and this is more not at all comprehensive, but just sort of a survey of the kind of challenges we're facing today, both globally and locally, that affects our ability to manage the Platte and to maintain the Platte in what we see as a desired state. And ultimately in this talk, I want to get to that question, desired states and alternative states for the Platte River. So we're in a challenging situation right now. Why sub-Saharan Africa? Because sub-Saharan Africa is driving global population growth in a very big way. We expect to have many more people to feed in very short time. I believe we just hit 8 billion people on the planet. That's quite a few. I don't remember how many were on this planet when I was born, but it was at least half that many. And so we're still experiencing pretty phenomenal human population growth. It's reduced. When I started my professional career, the estimate was by 2050 that we'd have 20 billion people on the planet. But because of a more rapid demographic shift in some nations and because of HIV, those population estimates are reduced, which is probably a good thing on a planet that's rather crowded right now. And of course, with increasing population, bringing this back to Nebraska and our agricultural production, we will have more mouths to feed, and much of the landscape, almost all the landscape of Nebraska is devoted to food production. And in fact, globally, much of the land surface of this world we live on, our only world, is devoted to agricultural production. And the exceptions are generally on very marginal lands. Everything else.
It's a little hard to hear.
Well, thank you. How's that? Wow. So we're pretty full agriculture. There's not a lot of land left to expand ag into. We have increasing populations. This obviously creates challenges for us, and it creates challenges in how to produce more food on these limited food production landscapes that we have. Grasslands in particular. Nebraska was a grassland state. It still is a grassland state, but if you live in the southeast part of the state like me, often when you're driving out in little country roads, you might think you're in a fully forested landscape. So we're undergoing transition in land cover as well as in land use. Of habitats or biomes across the world, grasslands are one of the most endangered. We have a very small percentage of grasslands left And those grasslands we have are under more and more pressure from human and other sources. So 95% of our tall grass prairie in eastern Nebraska and extending up the Platte, but also to the east of Nebraska itself, has been lost. And in general, grasslands of the Great Plains have not been faring well, and that challenges there are both agricultural production, but also what we see is the loss of resilience of grasslands and the transition of grasslands to woodlands in a moving wave that we're seeing come north across the Great Plains. And I'll get more into that in just a moment. So the global change, though, that we're seeing isn't a Nebraska change. It is, but there's global events going on. And just to highlight a few of those changes, we've had more land converted to cropland after 1950 than the 150 years or more before that. So land conversion continues. It's rapid. Coral reefs, sort of a sentinel, sensitive ecological system, are challenged. I believe it was 2 years ago that 90% of the Great Barrier Reef off Australia was bleached, and it looked like it's signaling the collapse of that reef. It's better this year, but there's some dire warning signals in oceans and reefs. Mangrove areas, which are critical for fisheries and also protective habitat, maintaining resilience of coastlines, have been threatened and are been reduced and continue to be reduced for a number of reasons, including for aquaculture, but a myriad of reasons. Water reductions or water withdrawals continue unabated, as you've seen from the Platte River itself. And I don't know if any of you noticed on the first slide I put up, you noticed on the right was a dry Platte. That picture was taken just a couple days ago by Craig Chandler and was published in the New York Times. And that's what the Platte River looks like right now in portions of it. I'll show that again in a moment. So agricultural production has to increase if we're going to feed additional mouths. It has to increase a lot. And again, Nebraska is an agricultural state. So how are we going to reconcile this need for further intensification of agriculture with the needs of fish and wildlife and habitat and ecosystems and the social systems on these landscapes? So the global changes that are occurring are global. They're not just Nebraska. They affect us. The stresses that we see are interacting often. So land use change interacts with the effects of drought and other things to intensify those effects. We can't think of them singly. When we talk about the Platte River, and Vesper Group and others have been talking about the Platte River a lot, there is no single generally causation. These are complex adaptive systems, and the challenges facing them are also complex. So the responses that we see are often non-linear. So we have slow change in the river, and the response of the river might be rather rapid. A sort of absurd example of that is we slowly reduce water volumes being released out of dams. At some point you hit a threshold and this water stops flowing down the river. And we need a framework to understand that change, and not surprisingly, I would suggest that that framework that may help understand part of the changes that we're trying to cope with is a framework of resilience. And resilience has been out there for a long time. Everybody's sort of familiar with it. It's been used at local and global scales. Probably a lot of you are familiar with the idea of global planetary boundaries. It's been put out by Will Steffen and Johan Rockstrom and others, and they've been refining this idea. But the idea here is that we are hitting planetary boundaries in terms of extractable and usable critical resources, including things like fresh water nitrogen and phosphorus, etc. So there's global challenges that are happening and impacting and interacting with our more local challenges. And our local challenges here are we have a complex Platte River Basin that includes ecological components here. There's lots of folks here concerned about the ecology of the Platte, but it also includes the social component. There are cities and rural areas where their livelihoods are entirely dependent upon the Platte. It's nice to see Kearney has a sign outside it saying the Platte capital, the crane capital, sandhill crane capital of the world, I believe is what it says. Great to see. So ecology, social systems, and economy all come into play into how we can manage this system, what our options are, and what are the trade-offs. Ultimately, we're in a system that's fully appropriated in many senses of the word, beyond just the use of water sense of the word. And so any changes we make are going to have effects elsewhere. Trade-offs are needed, and how we manage and navigate those trade-offs is important. It's important because while Nebraska is an extremely productive agricultural system, and Nebraska irrigated agriculture is arguably the most productive agricultural and efficient agricultural system in the world, what it hasn't had is a test of time. We really don't know how resilient this type of agriculture is. We're not really entirely sure for Nebraska, and there's much more uncertainty how this kind of highly industrialized, highly efficient, irrigated agriculture may or may not be resilient in other parts of the world where it's being exported. So there's some big questions there about resilience of our agricultural systems. And it's important because agricultural systems around the globe have collapsed over time. And they collapsed from a sudden loss of resilience. And we can go back for a few examples. Indus Valley in India, a change in the monsoonal cycle. In many of these agricultural collapses, you'll see a link to climate. So monsoon cycle altered over 2 centuries and led to a loss of agriculture in the Indus Valley, a collapse of it. See that in a well-known example that we're probably all familiar with, Mesopotamia, where salinization, because of over-irrigation, actually collapsed the cradle of civilization, if you will. And the Murray-Darling, to give us a contemporary example, Murray-Darling in Australia is currently undergoing a potential collapse because over-clearing and irrigation has actually led to a rise in their water tables. And that rise in that water table is eliminating their ability to conduct agriculture in much of the basin. If you're familiar with Australia, there's not a whole lot of arable land in Australia, so the Murray-Darling Basin is absolutely critical. So these kind of changes are happening. They're not rare, they're uncommon. But when they happen, they're extraordinarily consequential. And these kind of changes, these sudden losses of resilience and change, fundamental change of a system, which you sometimes sort of state as collapse of the system, have happened near to home. It's happened with the Dust Bowl, where we have the same sort of driving variables, a slow change, slowly increasing the amount under plow, amount of land under plow, and then a slow change in the climate, and then suddenly we reached a critical tipping point, and we went into the Dust Bowl. I won't go further into that event, but I will note that through sort of collective action and through following a real purposeful process of transformation, the Dust Bowl now is a very productive agricultural land again. So transformation is possible. Causes of collapse may be local or may be global. As I stated, climate change is often a slow driver. that'll lead to actually sudden abrupt changes in systems. But local small-scale changes can as well, like the overzealous cultivation prior to the Dust Bowl. So the change can scale up from small-scale changes like plowing, or it can come top-down from things like climate, either way. But it's important either way to know that when there is an abrupt shift in the social ecological systems we rely upon and live in, there's a difference in the ecosystem services that are provided. And because we have co-developed the natural resource systems that we live in now, any sudden change like that is likely to be undesired and come with a reduction in the goods and services that we rely upon or count upon. So it's in our best interest to avoid these kind of abrupt changes if we can. So these kind of changes are what we call regime shifts. Because of some slow change in the system suddenly changes to something very different. And there's examples of that across the world. When this idea first came out in 1973, it was critiqued that there were no alternative stable states anywhere documented in the world. And at the time, there was just insufficient longitudinal data, and now alternative stable states have been documented for almost every system in the world. And a couple examples, as stated, productive agricultural land, Dust Bowl example, with a change in climate and cultivation, flip to an unproductive Dust Bowl, if you will. Rangelands, an Australia example, overgrazing in particular in this case, leads to the loss of grass and the creation of a brushland. And again, that comes with a much different set of goods and services for humanity and loss of rangeland livelihoods. Places near us in the sandhills are undergoing a transition now. We're seeing a loss of grasslands and an eruption, if you will, or a transition of those landscapes from pure grass, wide open horizons, to being now cedar or forested woodlands, sort of following what happened in the southern Great Plains and what's happening in eastern Nebraska around my home now. I'll give you an example from some research we did do on the Great Plains, documenting these changes. Often when we think of regime changes, we think of a single place. Hey, it's the Dust Bowl, it's a location, it changed. Or hey, there's a shallow lake that was a clear lake. There was phosphorus input, and now it's a eutrophic lake. So those are points in space and time. But a lot of these changes are actually spatially contagious. So they move over time. So think of trees. It's really a tree invasion process, and the trees are moving northward from the southern Great Plains. So we did a little study where we didn't actually study the trees. This is a Platte River where cranes are important, and why we decided to study the birds of the Great Plains. We asked the question, can we statistically tell apart birds in the southern Great Plains and the northern Great Plains? Or is there just a sort of a Great Plains avifauna? Or is there a southern avifauna, a northern avifauna, or are there more than that? Talking to ornithologists, they do think of a very distinct southern and northern avifauna, but nobody's really looked to define that except in perhaps species lists. So we statistically took a transect from Texas up into Canada, 250 miles wide, and over a 50-year longitudinal time frame, and looked at bird communities along this transect. What we found out, you have to bear with me, is that this is latitude on the left axis. These are actually body mass distributions of avian communities. That's every bird in the community at each latitude. And you can see the square here actually is a statistically identified self-similar group of species that goes from 30 degrees latitude up to 38 degrees latitude. Above that, statistically, there's a different set of birds. If you buy that, then you can buy the rest of this. Over time, what we saw from 1970 to 2014, and it's easier if I put it here, was that that southern group of birds in mass is moving forward. So we have a regime moving. I know a lot of people who study ecology and climate change in animals thinks of each animal moving independently according to its climate envelope. So you have idiosyncratic movement of animals in response to climate change. I contend that's incorrect because animals interact with their environment and each other, and these systems tend to stay intact as long as they can. We document that here. These systems are moving north. There's where the Kansas border is. So you see this avifauna over a relatively short time has moved relatively far. And in fact, if you map the rate of movement at the northern edge and you map the rate of movement at the southern edge, the rate of movement is slower in the south and faster in the north, which is completely consistent with Arctic amplification for climate change. So we document that these things are moving. We also make the case that these animals are moving northwards in the Great Plains, having to do with obviously complex factors, many of which we don't understand, but partially due to the invasion of cedar moving up, this contagious invasion process moving up the Great Plains and changing the ecological system in ways that can be recorded not by just looking at cedars, by looking at the change in avifauna over time or other animals. So change is happening. It's coming here. And what does resilience have to say about that? In terms of resilience, I'd like just to say a couple things. I've heard the term used a couple times here, and it tends that people use resilience in one of two ways. And I'm sort of on a mission always to at least differentiate those two meanings for people so they're clear what they mean. So resilience has come to mean a rate of return. And I've heard it here today when people talk about resiliency, they're almost always talking about rate of return. What that means is the ability to bounce back. So if you have an animal population that's disturbed, crane populations drop down to 50 and then recover back up to 500,000, you can measure how long that recovery took and you have a rate of return that's very simple and very satisfying. But there's a couple other definitions of resilience that are much more rich as well. One is using resilience as a process. I won't talk about that here because you can use resilience as a verb saying enhance resilience, for example, and mean either meaning of resilience. But I'd like to focus on this idea of resilience as an emergent property because I think it's important because resilience as an emergent property captures resiliency ideas, which is simply if there's a disaster, recover as quickly as possible. So we often use these ideas, it's kind of use the term, well, I won't use it here, it's probably not politically correct anymore, but ball and cup heuristic, and the state of the system is a green ball. A disturbance comes and it pushes the system away from its equilibrium point. And so over time, post-disturbance, the system should recover. That's what you're measuring. It assumes that there's an equilibrium. It assumes the system is largely non-stationary. It doesn't change over time. And it assumes there's no threshold you can go over. So it's very enticing. And in reality, probably 90%, 99% of the dynamics of systems given perturbation or disturbance are this. They simply recover. And it's just how long does it take? But there's another set of situations that are much less common, but much more consequential. And that's the idea that there's these critical thresholds in systems. And when we exceed those thresholds, the system collapses, if you will. I don't really like that term, but fundamentally changes and organizes around a different set of structures and processes. And that gets us these regime shifts. Clear Lake, phosphorus, not clear lake, eutrophic lake. So given that definition, resilience is simply a measure of the amount of disturbance or perturbation a system can take before it flips to an alternative stable state. And it's important to realize that both desirable and undesirable states of systems are highly resilient. So saying that something is resilient is good is probably wrong, because something that's highly resilient can be in a very undesirable state. Think of those eutrophic lakes that we would like to make clear lakes. It's actually very difficult to make that happen because these systems are strongly self-organizing. These kind of dynamics were presented in 1973, but they were recognized a long time ago. So I like to throw out this Aldo Leopold quote. It's a public domain, once a velvet carpet of rich buffalo grass and grama, now an illimitable waste of rattlesnake bush and tumbleweed, too impoverished to be accepted as a gift by the states within which it lies. Why? Because the ecology of the Southwest happened to be set on a hair trigger, meaning that there was a threshold there, and it was exceeded. So it's very interesting to see those kind of terminology and those kind of things discussed many years ago. So Aldo recognized the change. So a regime shift involving alternative stable states occurs when a threshold is exceeded, when a controlling variable is changed in the system so that the feedbacks change and you get a fundamental change in the system. I won't go through an example of that except in the Platte in a moment, since I think that's most relevant to us. But I'll say that there's another way to show the dynamics of resilience, and it's sort of this, in a ball and cup diagram. If we think of this system, here's grass and shrub states. We're over here in the grass state, but we're approaching a threshold to go over into the shrub state. And these landscapes change as we modify them. So again, the emphasis on the idea that the systems we manage are very non-stationary. So it can make it very difficult to know what to bounce back to if we have ideas of bounce back. How far back do we go? Threshold responses are ubiquitous and have been around a long time. This documents the change in the Sahel when it went green, went brown rather, 5,000 years ago, the browning of the Sahel, having to do with actually solar radiation, slow change in that. We can see those kind of threshold response in ocean regimes too. This is zooplankton populations in the North Sea. We're given a climate change. You have a very sudden change in species populations. So to reemphasize, resilience is neither a good thing or bad, it's just a thing, because undesirable states of systems can be highly resilient, and then it's incumbent upon us to reduce the resilience of those undesired states. And those thresholds have been mapped out in agricultural systems a fair bit, but especially in sub-Saharan Africa, where there's been a lot of work in resilience. And it's been so much work because so much of Southern African agriculture has sort of been stuck in these what are called poverty traps, or there's a number of other kind of traps that have just been this series of sort of collapses in the system and changing to a new system with a sort of a loss of desired outputs over time. Very well mapped out for that system. So the Platte River, historically, and sometimes when we're here at 5 in the morning in March, presently, was a fantastic river, braided, scouring flows down the river, making plenty of habitat for cranes and waterfowl and all kinds of other animals. But we're people, and we manage our environments. And Nebraska, of course, being a state like many Western states with limited water supplies, underwent a series of water management decisions and building and structures over time, also to do with the rural electrification. But the end result is, I don't know that history is nearly as well as others. The end result is that we have a highly managed, highly engineered water system that's fully appropriated. So we have these pretty intensive canal delivery systems for agriculture. We have tons of pivot and other irrigation for crops along the river, taking water out. We have wells that are very abundant in this state, as you all know. We have a groundwater that's declined in places, not as bad as some other Great Plains states, but we have some water issues in this state. And the Platte River, has been pointed out earlier, is fully or over-appropriated right now. Platte River today, much of it looks like this. I would state to you that this is an undesirable alternative stable state for the Platte River. So the lack of pulsing flows, the lack of sediments has led to the armoring of the islands and vegetating of the islands and loss of the dynamic sandbar habitat so critical for our animals. And this is a highly resilient state, super resilient state. It self-organizes, and it's going to be difficult to make any change to the state. We try it though, and the Big Bend has lots of actions, and the PRIP, of course, and others have been undertaking lots of actions to maintain a 50-mile or so stretch, the Big Bend area, as in a state that it originally was, the original state of the Platte. And we do a pretty good job of it, not we, I'm not out there, but folks do a pretty good job of it, and crane populations, et cetera, are doing well. But I think, Rich, I'll ask you, how quickly would a sandbar in the river become non-usable habitat given the loss of management action? Yeah. Yeah, so a year or two, you'd get vegetation back on the sandbars. So what we're doing for habitat now to maintain the river in desirable state is basically farming it. First time I came to Nebraska, there were tractors in the river plowing it. That, being from Wisconsin, that puzzled me. So now I know a little better, but we're basically farming it, and we're maintaining a system in a desirable state for this small window, but it's fully coerced. It's a section of the river with no resilience. It would flip back. The propagal pressure from invasive species, the lack of water flow, and the lack of sediment would flip that section of the river back to a fully wooded, fully entrenched, armored island situation that's uninhabitable or unusable for cranes very quickly. But working in that section very strongly, doing some good work. It's really nice to see. We still do have cranes here. Populations look really healthy. One of our challenges in maintaining that healthy habitat and managing for cranes and other ecology on the Platte River is this idea of hysteresis that also comes out of resilience. Hysteresis, the way to consider it, is simply when the path out is different from the path in. This is actually a figure from Martin Scheffer's work in shallow lakes, showing as you put phosphorus into a shallow lake, it stays as a clear, shallow lake till you hit a critical threshold, the red up there, and the system suddenly goes into a eutrophic state. So great. Very easy to reverse, right? We just stop putting in phosphorus and we take out the amount we put in. But that's not the case in hysteretic systems. So what happens is you start, phosphorus gets down into the sediments, you start getting recycling of the phosphorus. You've also lost your rooted macroalgae because just the sunlight doesn't distribute anymore. And so you lose the ability to get macroalgae rooted. It's just much more difficult. And the reality is, to get the system back in a hysteretic case, you got to remove much more of that disturbance than it took to flip in the first place. So it can be really hard to restore systems because of hysteresis. And I would contend to you that the Platte River is strongly hysteretic. Let's say this is largely the kind of state that many of us would like the Platte to be in, back at sort of pre-colonial state. That's good habitat for cranes. And this is the current state. So if the system were non-hysteretic, we could just put a couple pulsing flows down the river and blow out the vegetation. There have been a couple pulsing flows down the river, both experimental and nature-based, if you will. And we didn't get back the habitat of the river. And that's because of hysteresis. To get this river back, we have to do what's been done, which is herbicide the invasive species on the sandbars, and then cut down the cottonwood, and then remove the cottonwood biomass, and then plow the islands to break up that root structure so the sand can move. Anyways, it's a very difficult process. And because we've lost those natural structuring processes, the flooding flows that used to come, all this has to be replaced through human management. And those areas that are still being farmed, if you will, gardened for wildlife habitat, are difficult to get back because they're so strongly hysteretic at this point. So one lesson there is it's much easier to maintain a system that's in a desirable state, to maintain it in that desirable state and not let it flip to an undesirable state, than it is to try to get a system back. So I might ask everybody if the Platte River isn't in a trap right now, or at least the Big Bend. We're not in an undesirable state. I'd say we're in a desirable trap that is difficult to get back into. In other words, we're in a situation where perpetual management, until we figure something else out, perpetual management is absolutely necessitated. And that's going to continue to be as expensive as it is now, and may actually get more and more expensive as those water flows from the Colorado Front Range and Wyoming reduce over time with reduced snowpacks. There is some hope, is that transformation is a sort of human agent-driven process of reducing the resilience of a system purposely and then making it collapse, and then helping it, when it reemerges, fostering its emergence toward a desired rather than the undesired state. And there's a lot of work in the ideas of transformation that I won't get into now, but is possible. And we've done transformation on large scales before. In this region, the Dust Bowl transformation, very agent-driven by humans, and very successful in this case. Regardless of what we do, is one thing we learned from 50 years of working with social ecological systems and resilience, is that there's always surprise. Back years ago, you might have remembered a Rumsfeld, I think I just recently heard it, Rumsfeld quote that said, there are no unknowns, there's unknown knowns, there's known unknowns, there's unknowns we don't know, and anyways, it didn't make sense to many people, especially how I quoted it, but it actually made a lot of sense to those of us who work in resilience. The surprise always emerges. And so something to keep in mind, as the Dust Bowl was perceived as a surprise to people here who experienced it at the time. So I talked a lot about desirable and undesirable states, but what those are is a human value question. And in fact, much of the Platte River that I sort of described as undesirable is in many ways desirable to much of the state, because the Platte River is producing food, and it's really critical for that, and that water is very useful for that, and we have a very productive agricultural system. but there's folks in this room too, and 500,000 cranes for whom that state of the Platte is undesirable. So how we reconcile those is really a human question, not an ecological question. And keep in mind there's alternative states for the Platte. I think of a wooded state or the open sandbar state, but there's that third state possible too, which is just a totally dewatered Platte that we've been seeing the last couple of weeks. So what do? Foster resilience in desirable states if we can. Foster a return to the original state, again, if we can. It's difficult in a situation where we're over-appropriated. Foster a transformation to something different that's desirable for us, if possible, as well. We have choices. Some of us value this state of the river, but this state of the river, again, taken last week, is also a possibility, and perhaps one we wish to avoid. So ultimately, it comes down to human choices and what we wish to do with this river and how we get there, and really how we make those trade-offs that are so critical between sort of the agricultural needs and the ecological needs of this river, which are very difficult, and they're not really ecological questions. These are human questions. So I'm really happy to see the social scientists here in the social science session this morning. Thank you. If there's a question, I'd be happy to take them.
Dr. Allen, thank you. I'll ask a question if nobody else is going to. So, in your presentation, you talked about basically pushing the Platte back into a more resilient state. So the things that I heard for activities to do that is to do what we're doing now, but at much higher intensity, or what's the part of that I'm missing?
Repeat the short version of the question.
So the question was, how can we manage the Platte back to a desirable state? And of course, desirable state would be particular probably to the folks in this room, because what's desirable may differ amongst people. And to be honest with you, I think that's probably one of the biggest challenges right now, is that what's a desirable state of the river varies across two pretty significant user groups. And reconciling that and managing those trade-offs and what we do where, I think, is probably the biggest challenge.
So what about the state that you presented as your desirable state?
Can we get that state back at a large scale? I think, we grapple with that. I think at this point it's difficult simply because of over-appropriation, not enough water in the river. So we did manage it intensely, and it coerces that desirable state, and that works for now. I don't know how long that can work for, and I sort of feel like we're in a holding pattern over time until we can really figure something else out that's more desirable for both groups. Yes?
Okay, so there was that slide that talked about the, where you had plowed up everything to disrupt the cottonwood roots. And how disruptive is cottonwood?
How what is cottonwood?
Disruptive, or is it like a noxic tree? It seems like those are slow
Yeah, I mean, I guess the cottonwood is like anything else. It's great until it's somewhere where you don't want it. And, you know, the problem in the Platte River, of course, especially when it's right in the middle on the islands, is it changes the structure that the animals interact with and makes those islands unattractive and unusable for roosting cranes. So undesirable from that sense. Otherwise, it's a great tree. But trees, especially in the middle of the river, are difficult to deal with because of the biomass and the root structure, et cetera, that's there. It's tough, and would be disruptive to move them. Yes?
Are there, or do you know of any river systems that have documented hysteresis and that have maybe thresholds in one direction that are different and thresholds in other directions, where that has either been documented or where they've been able to even reverse a system?
Yeah, I think it's yeah, are there other river systems that are hysteretic and where this been able to reverse the undesirable state to a desirable state? I mean, I'd say, many alternative stable states and systems are hysteretic. So almost anywhere where you see an alternative stable states, you have at least some degree of hysteresis. It's very strong in the Platte. I was part of a governance of water systems working group for many years that ended a while ago, and there are some river basins that are effecting change that will help make those rivers more dynamic and sort of self-organizing, that is, their own processes maintain themselves in a desirable way, sort of parts of the Danube going through parts of Eastern Europe where riverbanks have been moved, or levees have been moved back, and natural flooding is done, and now the agriculture has been developed that actually works with flooding, so going back to the old historic ways of doing ways in parts of say, Austria area. So one example, but I'd say generally that hysteresis is a huge problem. Big problem in river systems and big river systems where water is limiting are special problems. And that's our challenge here. Well, thank you, and look forward, Chittaranjan. Last question for you, Chittaranjan.
So you said to somehow restore these sandbanks. Has anybody looked into doing hydraulic model studies? What amount of flow, or if the Kingsley Dam has the capacity right now to really release enough water to wash off those trees, but at the same time, what happens with the infrastructure, the bridges and all that?
It's a good question. I'm sure there's some people here who have the answer to that. I'll repeat it, which is, have there been models that have estimated the amount of flow out of Kingsley necessary to actually provide sufficient scouring? And we won't address the question if that's with management to remove trees, et cetera, or not. But how much water would that be? Could we do it? And also, would that affect the human infrastructure, bridges, et cetera, downstream on the river? Anybody have an answer to that?
Yeah, so 13 to 15,000 CFS for 40 days plus will widen out the channel. Anything less than that doesn't have it. From a Kingsley perspective, you can let all kinds of water out of Kingsley. The biggest issue is that over about 3,000 CFS out of Kingsley, you start creating issues in North Platte. So that's so you go over flood stage and you're basically limited.
So we're constrained by those downstream impacts.
Can you remember the numbers well enough to repeat it for our online people?
I believe the CFS required to 15,000. I had that, but 15,000 over a number of months to be 3 days. 40. Okay, got it. 15,000 CFS, 40 days to really get the sandbars mobilized, but at about 3,000 CFS, North Platte starts to have flood problems. So therein lies the problem. Well, that was a depressing end, but.
Well, thank you for the humor as we're reminded this morning. Let's thank Craig again.